Let me share my screen so let's start the class. My screen visible?
Yes, sir.
All right, so let us start discussing about today's class about process synchronization. In the previous class, we discussed how a process is uh, created, how the process is scheduled using CPU scheduler, various approaches for CPU scheduling algorithm, like first come first serve, priority scheduling, round robin scheduling, shortest job first, shortest remaining time first. All this scheduling process, how process are scheduled, we discussed. Also after that, we discussed how process are created, how process are terminated, what are the various commands that are used. We can do that by ourselves in Linux environment. We discussed that, like fork, exit, some system calls. Now we will try to continue our discussion on process synchronization. Also, when we try to discuss about inter-process communication, that one process will communicate to other process, we discuss that there are two communication models. One is shared memory, that process A will write something in shared memory and process B can access the same memory when two processes are sharing the same memory space, or else when process A is trying to read from one end and process B is maintaining a message queue, message passing, and this is also another method where uh, process A and process B will communicate through this message queue, what is communicating from A to B or B to A. So using some queue, this will happen. So inter-process communication can happen using some system calls like pipes, semaphores, monitors, mutex locks, and so on and so forth. We will try to discuss few of them in today's class. The main problem when it comes when the inter-process communication, when the process are communicating with each other, provided that the shared memory or a message queue, there are some problems that will arise. We will try to discuss that today. The main problem is synchronization. So when communication happens between processes takes place through calls like send or receive primitives, there are different options for implementing the send and receive primitives. For example, when message passing may be either blocking or non-blocking, also known as synchronous or asynchronous. This could be one way, that when I say block send, which means that the sending process is blocked until the message is received by the receiving process or by the mailbox, whereas non-blocking send is the sending process sends the message and resumes the operation. Means uh, this is slightly different, but the technical definition, or put the words if you have to put it, like blocking send and non-blocking send, likewise blocking receive or non-blocking receive, can be defined in the given statements in the slides. Blocking receive says that the receiver blocks until a message is available. Non-blocking receive is the receiver retrieves either a valid message or a null. So it's a very slight difference, but uh, like the blocking or non-blocking can be compared with synchronous or asynchronous. The idea is like we will try to see that with a simple example, producer and consumer problem. Um, Producer will produce the item and consumer will consume the item. As long as there is no production, consumer cannot consume the item, right? In order to consume, you have to produce. If all the items are produced by consumed method, then this method consumption will go in wait to get some more data that has been produced, that has to be produced. Likewise, um, when the production is, suppose we are maintaining a queue and all the queue is full, all the production, the items that needs to be produced for the moment is full, then the production will not happen until it is consumed. So the production will stop till the consumption continues, right? If consumption takes place. So this is one important idea where the same way the sending and the receiving will takes place. If I have to send some information, it has to be received. As long as it is received, then only the information will be sent again. If the send queue is full, then until all the messages will be received, then the no messages will be sent again. It will be stopped for a while. Likewise, whatever the message is sent, it will be keep consume. It will be keep consumed. And if there are no message to send, the consumption method will keep on waiting for the next items that will be consumption. Okay. The main thing what it comes when sending a message or receiving a message is buffering. Buffering is like when whether the communication is direct or indirect. Messages can be exchanged by communicating process reside in a temporary queue. So these queues can be implemented in three ways. One is zero capacity, bounded capacity, and unbounded capacity. Zero capacity means the queue has maximum length of zero, which means that link when cannot have any messages waiting in it. So in zero capacity, there are no waiting messages. There is no wait. As long as it produce, it will consume. As long as it will, there is uh, uh, no waiting period. Okay. The sender must block until the recipient receives the message. So in this case, the sender will block until recipient receives the message because there is no capacity for waiting messages. Bounding capacity, it will maintain a queue length of n. So n messages can reside in the queue waiting to be read or waiting to be received. If the queue is not full when a new message is sent, the message is placed in the queue, whether it might be copied or kept as a pointer, and the sender can continue execution without waiting. The link capacity is finite, however. If the link is full, the sender must block until the space is available to the queue. This is bounding capacity. Unbounding capacity is the queue length is potentially infinite, means a large queue is maintained. So number of messages can wait in it. The sender will never block. So in the first case, the sender will block until the message is received. There is no waiting period. Bounding capacity, there is a length of n. So n messages can wait. Uh, the sender will continue to work till the queue length is full. After the queue length is full, then the sender will stop until the queue becomes empty. Some space is available in the queue, then it will be produced. In unbounding capacity, you are assuming that the queue length is much large. Potentially infinite means very big. So the sender will never block. Always there will be some space where when sender produces something, there will be some space to receive. These are the three ways where the buffering will work. Having said that, let us try to talk about process synchronization. The process synchronization happens. A cooperating process can affect the other process executing in the system, either directly or by a logical address space. When it is shared by using a shared, I mean, when the data is shared, when the data is allowed to share through shared memory or message passing. So in operating system, the number of process are executing can is more. There will be more number of process, concurrent process are executing. They all share the data using the shared memory or message passing. When they try to access, it may lead to inconsistency. So in order to avoid this inconsistency in a cooperating process, when they share the logical address space, we need to maintain the data consistency. Hence, the process synchronization will happen. So let me tell you one example. Let us see this example. Suppose when a producer item is produced and when the consumption item is consumed, this is the logic code. So when the count is equal to buffer size, then we will maintaining a blocking buffer. So we will do nothing because buffer size is maximum. We'll keep incrementing the counter. When the counter is equal to buffer size where you are maintaining the queue, will not do anything. But if the count size is not equal to buffer, then we will produce the item. That item is placed in buffer, and we will increase the buffer size capacity and increment the counter, right? So this is the simply producer code. On the other hand, consumption code, when count is equal to 0, means there are no items to consume. We will not do anything. If the count is not equal to 0, then whatever the buffer item produced which is placed in the buffer, that buffer will be consumed. The item next consumed will be from the buffer, then output buffer size will be incremented and the count will be decreased. This is a simple code for producer consumer problem. Okay, is this make sense? This producer consumer problem. The produce an item is next produced, consume the item that is next consumed. Is it make sense? Up to this part.
Yes, sir.
This part is clear. This is simple producer consumer problem. This is production. When the buffer size is equal to count, means the queue is full. We will not produce anything. We will take, if the count buffer size we have empty which is not equal, then we will produce next item, keep in buffer, increase the buffer size, increment the counter. Now if the count is equal to 0, which means the queue is empty, there is nothing to consume, or else if the queue has some item, then we will consume from the buffer, will increment the buffer size, and we will keep the will decrement the counter. This is simple producer consumer problem. Now let us assume that if count is equal to 5, let us assume that if count is equal to 5, then what happens when one count plus plus happens, and what happens when one count minus minus will happen? What is the value of count after count plus plus and count minus minus? After one produce, after one output is consumed, suppose if count is equal to 5, this count plus plus will become, if count is equal to 5, what will happen when one item is produced? This will become what? Count plus plus will become 6, correct?
Yes, sir.
Okay. What happens when one item is consumed? What happens to the count value?
Sir, 4.
No, here item is 6. One item you produce 6. You are
So then
consuming
5.
one item. It is 5, correct?
Yes, sir.
So initially, if the count is equal to 5, you are producing one item and you are consuming one item. When you are producing, the count will increment to 6. When you are consuming, again the count value will become 1, 5. Okay.
Yes, sir.
Does this make sense?
Yes, sir.
Okay. Now let us assume that this count plus plus, count minus minus, what we are writing in C programming, ultimately it is converted into assembly language at the processor execution level. Now assume this count plus plus is written in assembly code language in 3 statements. So there is a register memory with a count. You are incrementing the value of register by one value, and you are storing that register into the count. This is how the count plus plus works in assembly programming language at the processor level execution. The register memories are which are resided in the motherboard, I mean the processor, where it will be accessible by the processor when it is executing. Similarly, count minus minus in assembly language will be executed. Count is equal to register 2. Count register 2 minus 1 will be stored in register 2, and register 2 will be stored in count. This count minus minus 1 statement is categorized, I mean classified into 3 statements of assembly programming language. Does this make sense?
Yes, sir.
Okay, this is count plus plus. Simply I'm writing in assembly programming language in the very bottom level. Now let us assume these both processes are executing concurrently. Means after this statement can execute this statement. When two processes are put in execution simultaneously, any process can execute at any time because of concurrency, right? So after first statement, the second statement may execute. After second, maybe this two will finish, then it will leave, then any order of these three statements from count plus plus, count minus minus may work, execute in any order. Now let us assume that at t0 time, uh, producer will produce the item. The count value is 5. Again, we will start with say count C O U. Here the count value will start with 5. Okay. So the one increment, see, one produce, one, two, three, and one consume. We are producing one produce and one consume. Ideally, we discussed here after one production and one consumption, the value of count should again come back to 5. One item will produce, the count value will increment to 6. One item will consume, then count value will become to 5. This is the ideal way how this will execute. When concurrent processes are coming, then assume that say T0 producer will produce the item register count is equal to 5 to the register 1. So 5 will be stored in the register 1. At T1 time, register will be incremented by the producer process. The process producer will execute, register value will increment. Now the value of count register 1 is executed into 6. Now this process of producer will interleave. Let us say the consumer will start executing because of concurrency, simultaneous process. The consumer will come into the picture. Now the count value, what is the count value? The count value is same because after incrementing this register value, it is not stored again into the count. So the count value remains 5. The consumer will execute one more statement by decrementing this value. Now the count value will become 4. Now when register 1 is storing into the count, this value will become 6. The counter register 2 will store its value into the count. Count value will overwrite. Now the count value is 4. What is the actual value it's supposed to be? What is the actual value of count should be?
So it was 5 initially, right?
Right. It should be 5 because actually you are producing one item and you are consuming another item. So the production should increment to 6. Then after 6 you should decrement. This statement, this statement, after that this value should come. After this value, this statement should come. Because of concurrency, the both process is manipulating the same variable. Producer process and consumer process is manipulating with the same variable count concurrently. Because of this same variable shared value, we are getting a wrong result. The result we should get is 5 because you are producing one item and you are consuming another item. From 5 it should go to 6. From 6 when you consume it should come to 5. But at the end of the result we ended up the count value as 4. See, the both process are trying to manipulate the variable count concurrently. We are getting the wrong result of count value. Actual the count value is 5, but we are getting 4 because of concurrent process. Because the two process are not synchronized. This happens because not synchronization. You got it right? This this two process is not synchronized. That's why we are getting the wrong result. The correct result should be 5. So we need to do something, come up with some mechanisms when such shared memory comes or when multiple processes execute concurrently, the process when it is executing should be synchronized. Is this clear?
Yes, sir.
Yes, sir.
Okay. Now let us discuss. That is a problem, like where when a situation when several process access and manipulate the same data concurrently, the outcome of execution depends on the particular order in which the access takes place. This is called a race condition. Here, producer and consumer process, they went into a race condition and they tried to access and manipulate the count data, which leads the race condition to an invalid process synchronization. Okay, so this is called race condition because two processes went in race to finish their execution rather than giving some time to the process which executed first, which executed second. So to guard this race conditions will leave us in a tricky place because of uh, shared memory, and this race, as we can see from the above example, this race condition uh, will manipulate the variable count, and we need to ensure only one process at a time can manipulate the variable count. To guard against this race condition, we need to ensure only one process can manipulate the variable count at a time. To make such guarantee, we need to process the synchronized in some way. So that's where the process synchronization will come into the picture. So we will try to understand critical section problem for ensuring the processes are synchronized. Assume that a system consists of n processes like P1, P0, P1, and so on, Pn minus 1. Each process has a segment code. We call that as a critical section in which the process may be accessing or updating or data is shared with at least one another process. Now, the important feature of the system is that when one process is executing in its critical section, no other process is allowed to execute in its critical section. Okay, that is, no two processes are executing in their critical section at the same time. Only one process will execute or manipulate or update the data in a shared with another process one at a time. This is called critical section. Is this make sense?
Yes, sir.
I repeat it. You can understand this one more time. Each process will share the segment of code. We call that as a critical section. It may be used for accessing or updating the data with another process. When one process is executing in the critical section, no other process is allowed to execute in its critical section. No two processes are executing in the critical section at the same time. Okay, so this critical section problem we will define like this. So each process must request a permission to enter into the critical section. So it will request a permission to enter into the critical section. The section code implementing by this request entry section. So when this is true, whether you want to enter into the critical section or not, we will check by providing a request permission, and the critical section may be followed by exit section. The remainder code will be in the remainder section. This is a simple critical section problem. This critical section problem, only one process will execute at a time. Okay, so we will provide with a simple flags like entry section or exit section to make sure that the process, when it is in the critical section, only one will work at a time. Now, as I told, the solution to the critical section problem should satisfy three requirements. One is mutual exclusion. Mutual exclusion means if a process PI is executing in its critical section, no other process can be executing in their critical sections. This is mutual exclusion property. Progress. If no process is executing in its critical section, some process wish to enter the critical sections, then only those processes that are not executing in the remainder sections can participate. Okay, in deciding which will enter into the critical section next, this selection can be postponed indefinitely. Some progress should happen when the process which is in the remainder section, suppose here also there might be some other process, they will decide which will go to the next critical section if there are no process in the critical section. That is progress. Okay, you can see this. If no process is executing in this critical section, then some process wish to enter into the critical sections only that are not executing in the remainder sections can participate, deciding which will enter into the critical section next. Then there is a bounded waiting. There exists a bound or a limit, the number of times that the process are allowed to enter into the critical sections after a process has made a request to enter this critical section or before that request is granted. So number of times that other process are allowed to enter into the critical section is bounding weight. These 3 points, these 3 requirements should satisfy in order to provide the solution for the critical problem. Critical section problem. Is this clear? You can read these statements once. If you have any difficulty in understanding, let me know. Shall we go ahead?
Yes, sir. Yes, sir.
Okay. Now let us understand with a simple example. The race condition happens. Suppose there is a process P0 and process P1. Process P0 calls a fork, creates a new child. Process P1 also calls fork and creates another child for P1 and P0 respectively. Now, when a child process is created, it has to assign a unique ID. We call that as a process identifier, PID, and assume that next available PID is 2615. If you, because of the race condition, and this one process PID is available, P0 child process, P1 child process, if it is assigned the same process ID, because of race condition when assigning into PID, this should not happen. Because two process should not share the same process identifier. This is the main problem of mutual exclusion. Okay, mutual exclusion means each process should consist of unique ID. Mutually they should be exclusive, they should be not same. You understand what is mutual exclusion? See this? No other process can be executing in the critical sections means when the process ID will be assigned same, this should not happen. Each process ID of the child should be different. They are mutually exclusive. This should not happen. Sometimes because of race condition, when the process ID is assigned to the both childs at a time, then they are not mutually exclusive. This should not happen. Okay. So how we will implement critical section? There are two methods we will discuss. One is mutex locks. There are hardware based solutions to the critical section problem, but they are complicated and generally inaccessible to the application when we are doing some programming. So when we do an operating system, we can develop a high level software tools to solve the critical section problem if there is any problem, right? Because of software, we can write codes and we can manipulate. So one such software problem of critical section is mutex lock. Mutex lock is mutual exclusion, short for mutual exclusion, MUT, exclusion EX. First 3 words are from mutual, 2 words from exclusion. We have taken as mutex lock. The simplest, very easiest tool is mutex lock. Process when it is entering before the critical section must acquire the lock before entering into the critical section. It releases the lock when it exits the critical section. For example, when you are asked to use a room, only one person should be stay in the room. The simple thing you do is you take a lock, you lock inside, use the critical section room, and when you are coming out, once your job is done, you'll unlock it and exit from the critical section. Okay, so that's a simple example how the same idea is used in mutex lock. So the acquire function acquires a lock, the release function releases a lock. So before entering, when you're executing into the critical section, you put a lock, enter into the critical section, release the lock, then the remainder section will execute. The acquire lock will be when when critical section is available, or when a flag, you use a simple flag available. Okay, if available is true, then you enter into the critical section, make available false. Okay, if the definition of release, then turn this available to true, then whenever next time when any other process want to enter, it will check whether the available is true or not. If available is true, then it will acquire, make available false, making sure that the critical section is occupied by some process. If it is released, after releasing, this available will become true, then the next process will continue its execution. Is this clear?
Yes, sir.
So what happens in producer consumer problem? Producer will go acquire the lock, make the flag available false. So it will continue its execution after finishing all these statements from the producer. Then the count value will increment to 6. Then after that it will release the lock. Then the consumer will enter into the critical section. It will consume one item. Then end result will be again 5. So simply like your room, when you're going and entering into, you're locking it, no one is allowed. When you're coming out of it, you close the lock. Okay, that's the same logic where mutex lock is works, when only one process will be executing in the critical section. Okay, so the main disadvantage of mutex lock is busy waiting. Means when a process enter its critical section, any other process that tries to enter its critical section must loop continuously in the call acquire. Okay, the other people, when they want to enter into critical section, they will keep on waiting and keep looping continuously. When the critical section is available, they have to loop continuously. This is called busy waiting. The main disadvantage of mutex lock is busy waiting. This is like there is only one room, but there are so many processes are executing, right? For example, 100 processes are waiting in the outside of a door, and there is only one room. The other process will keep on continuously verifying. Thank you. Thank you. I'm sorry, guys. So the other process will continuously loop in the call of acquire. So this busy waiting is one of the main problem in the mutex lock. So this continuous looping is a clear problem because multi-programming, when it comes to multi-programming, when a single CPU core is shared among many processes, then only one process will enter in critical section, then other process will keep on waiting. So this busy waiting for checking whether the critical section is available or not wastes CPU cycles, and that other sub process may be used productively. This other checking time can be used productively for some other work. So this is the main disadvantage of mutex lock. To overcome this disadvantage of the mutex lock, we will go to another method of critical section called semaphore. So a semaphore S is an integer variable that apart from initialization, it is accessed only through two standard atomic operations, wait and signal. Okay. You understood what is the mutex problem, how mutex works. You put a lock, enter in the critical section, you release the lock. Other process will keep on waiting to take the lock. Unless the lock is released, the other process cannot enter into the critical section. We are achieving the process, we are achieving the process synchronization, but the disadvantage is the other process in a multi-programming, many process in a single CPU core, if it is available, then the busy waiting is the main problem because only one lock is there where you can enter and do your job and come out. Is this clear? Guys, are you there? You want me to repeat this idea?
Yes, sir.
See, in mutex clock, it's like whenever you are entering, see, in critical section, only one process should execute at a time. Is that clear? In critical section, only
Yes,
one
sir.
process should execute at a time. How we will ensure only one process will execute at a time is when a process entering into the critical section, it will lock before entering into the critical section, it will put a lock, and after finishing its job, it will release a lock. Is this clear?
Yes, sir.
How the lock, acquire lock and release lock will happen, which is a simple code which I have written, which is given with a simple flag. The acquire will check a variable available. Okay, if it is available, then it will enter into the critical section, it will execute its statements, make available false. So when available is false, when next process will come into this critical section, it will check the flag available whether it is true or false. Okay, if it is true, then it will enter. If it is false, it will not enter. Okay, now when this will become true, when available will become true, only if this process will change its flag to true. When this will be true, when it release. The definition of release is the value of flag will be changed to true. When the available is true, then the next process will enter into the critical section. When a process enter into the critical section, it will make the available false. Means this false is like locking the door. This true is like unlocking the door. It's a simple comparative. With simple variables, we were assigning and making sure that this will work. So when a process entering into the critical section, before that, it will check the availability. If it is true, means the some process released, it is available, it will enter into the critical section, make available false, making sure that if other process will come and check, it will check the availability. If it is false, then it will not enter the critical section until it will become true. When it will become true, only this process will release it. Is this clear?
Yes, sir.
Now, when one process enter into the critical section, other process will keep checking whether available is true or not. Correct?
Yes, sir.
When other process has to keep on checking. This is called busy wait. The busy wait says that when a process enter its critical section, any other process that tries to enter into critical section must loop continuously in the call of acquire. It will keep on checking to acquire to enter into the critical section. Suppose in this case, the producer enters into the critical section, the consumer cannot enter, the consumer will keep on checking whether the critical section is available or not. It will keep on checking whether the available critical section is available or not. So the consumer will go in busy waiting. It will keep checking busy and it will keep waiting. Busy waiting means continuously looping to make sure that critical section is available or not. Okay. So if you can compare this with a simple example, I will tell you that imagine this is a very bad example, but you can understand very nicely. You all people stayed in hostel. You in each floor there are toilets are available. Imagine that only one toilet is available. Remaining people will keep on waiting on the outside when this guy will come out, when this guy will come out. The people will be busy waiting outside because entering into the toilet is like entering into a critical section. Okay, imagine that. Don't write this in exam, and don't tell anywhere in the interviews. But for you to understand, I'm telling you. You enter in the critical section, you lock the door. Once your job is finished, you come out. But other people who are waiting in the queue will be keep on busily waiting when this job, whether it is available or not. The other guys will keep on checking, right? So that's what called busy waiting. Busy waiting will keep wasting. When a process will do the job, the process, how it will make sure that the critical section is available or not, it has to keep checking whether it is available or not. It will go in continuous looping to make sure that it will acquire the critical section. So this is called busy waiting. So in mutex locks, there is only one lock and one there is only one lock and where you can lock, enter into the critical section, come out. This is the big problem. Now, semaphores, on the other hand, will be like multiple toilets. You can do two, three, four toilets. If one toilet is busy, you go to the next one, next room, third room, fourth room, like that. You can keep multiple critical sections. Okay, semaphores is one bigger than mutex lock. Mutex locks will have only one lock that you'll lock it, you will enter the critical section, you'll come out. But semaphore is an advantage is it works on an integer variable that you can have multiple semaphores, multiple waiting rooms, multiple critical sections where you can carry out your operations, that is using wait and signal. So the wait and signal is given as follows. When semaphore S value is less than or equal to 0, which means you have to wait for some time, the critical section is busy. Then after coming out, you can decrement it. The definition of signal will make sure the definition of signal says that the semaphore is available, or you can increment the signal. So I will tell you this example, semaphore usage, how it will work. Operating systems, for example, let's see that one example I'll tell you. See this, how this wait and signal will work. When semaphore S is 0, then there is no resource available. When semaphore S is 1, exactly one semaphore resource is available. When semaphore S is equal to 2, 2 S resources are currently available. Okay, so these are the way we will understand that. So wait says that if S is greater than 0, then grab it and enter into the critical section, decrement the S by 1. Signal says increment S by 1. So you can have multiple critical sections using semaphore, because semaphore doesn't work as a mechanism simply by lock and acquire lock and release lock. It works with the integer variable where we can perform the uh, critical section problem in two standard atomic operations. Okay, so that's what the meaning, right? So the operating systems, when it can be defined, semaphores can be two ways. One is counting semaphore and binary semaphore. The value of counting semaphore can range over an unrestricted domain. The binary semaphore can range between 0 and 1. Okay, when a semaphore is a binary semaphore, which will range between 0 and 1, either 0 or 1, which is nothing but similarly to the mutex locks. Mutex lock works with lock and release. Similarly, a binary semaphore is a mutex with only 0 and 1. If you implement a semaphore with only 0 and 1, it behaves exactly like mutex locks. But in semaphore, you go for counting semaphore, you can have many number of a range over an unrestricted domain. The systems that do not provide mutex locks, binary semaphores can be used instead of providing mutual exclusion. Okay, if the system is not having the mutex locks, then binary semaphore will be used as a mutex lock. Is this clear?
Yes, sir.
Okay, simple. Semaphores are counting on binary. Binary semaphore is same as mutex locks. Mutex lock works like lock, acquire lock, release lock. Same way you can implement a binary semaphore in 0 and 1. May 0 means like you enter into the lock, make turn this 1. When until it's 0, then you don't enter, something like that. But semaphores you can implement with counting semaphore. You can have multiple semaphores. So one example I told you here is when semaphore s is equal to 0, then no resources available. When s is equal to 1, one semaphore is available. This is mutex lock. But semaphores you can implement in 2, 3, 4, so on and so forth. Uh, depends on your implementation. So semaphores can be integer value. If it is 2, then 2 semaphore resources are currently available. So wait will say that if s is greater than 0, then you enter into the critical section, decrement the s value by 1, means one room is occupied. There is another room. And after finishing your job, you signal increment the value of s. After incrementing the value of s, you will make sure that the semaphore is available to enter into the critical section. When the semaphore value is 0, then there is no resource available. When the semaphore value is incrementing, means the semaphores are available. When wait, then grab it, decrement the s by 1. Okay, so when semaphores are greater than 0, when it is 1, then the resource is used, the process will enter in the critical section, it will decrement to 0, the other process will not enter. When it is s is equal to 2, then one process will enter the critical section, the other process will enter into other critical section, and they will execute. So there are two critical sections here. That's how we will implement multiple critical sections using semaphores. Is this clear?
Yes, sir.
Yes, yes, sir.
Okay, so the simple code for how we will define semaphores weight and signal is we will keep a variable when s less than or equal to 0, means we will decrement the value, this is weight. The signal is we enter it and increment the value. The same idea what we have said here is the same that I mentioned here. Okay, now let us try to understand some case studies. Running process with precedence constraints. For example, I want to execute process P1. This is, say that process P1 has two sections, section A and section B. Process P2 also has section C and section D. Now I want the process 1 should execute completely. After that only process P2 should execute. Now what I'll do, simply I will write a semaphore, I mean few constraints. Okay, for example, B precedes C, that is B should finish before C. Okay, when C starts, before that B should proceed. So this section should finish first before starting C section code. Now what I will do is I will write semaphore S here. After semaphore, I will acquire the semaphore wait here, because this section has to wait. This section will keep on waiting. Then after finishing this semaphore, I will give signal S here. After giving the signal S, till that period, this process P2 will wait. After giving the signal S, then only this process will execute. So I will put wait here and I will keep signal here, which will make sure that this process will complete up to this point till the signal comes. As signal comes, then the next process will start executing. Okay, so in this case, A and B will execute first, then after that C and D will execute. Is this clear?
Yes, sir.
Okay. See, imagine you have a railway station. In railway station, sometimes uh, imagine you have only two tracks. Okay. Imagine railway station, you have two tracks, and an local passenger is coming and an express is coming. And as a train master, you will allow the express to go first. The passenger train can wait for some time. Okay, so you will make that the passenger train to wait and the express to go first. So you will not give signal to process P2, that is a passenger train, until the express will pass. The express train should go and it will give a signal. Till then, you have to wait in the for your turn to leave the station. A simple example. Okay, so B precedes C, simply like signal and wait. When I want make sure that B will finish before C, I will make the C wait until I'll give the signal after finishing B. So after finishing B, I'll give the signal, then the wait will start executing. So this is simple semaphore. Only I'm using one semaphore. Now let us assume that P1, P2 will not overlap. Means in the previous example, I make sure that B will finish first before C. But in this example, P1, P2 will not execute at the same time. So when I start process P1 and P2, P2 may start first. Concurrent execution, we don't know which process will come first. So P1 may execute first or P2 may execute first. So imagine that P2 want to execute first, then I have to make sure that P1 should wait. If P1 is executing, then I have to make sure that P2 should wait. Both process will not execute at the same time. P1, P2 cannot overlap. So in this case, I will take semaphore 1. I will make wait process wait for process P1 and wait for process P2. Then I will give the signal to both of these guys. Whichever the process execute, suppose process P2 will execute, this will call the semaphore S value as a wait, then until it finishes, the signal will come. This will not execute. Or if process P1 is executing, it calls the wait signal first, making the other process wait. Then this will finish its critical section. It will give the signal. Then the next process will continue. Any process may execute anytime, but they should not overlap with each other. In that case, I will use simply semaphore 1, whichever enters the first process. Suppose process P1 enters first. When wait happens, what will happen? S value will be decremented to 0. S value will be decremented to 0. Then the next wait, it will not work. It will enter in the critical section. After signal, S value will increment to 1. Then wait signal will say that, okay, my waiting period is done. After signal S value is incremented, then P2 will execute. Suppose P2 will start executing first, then the semaphore is grabbed by P2. It will make the S value 0. The other process will keep waiting until the S value is incremented by the signal. S value will become 1. Then only the process P1 will execute. So in this case, which of the process will start executing first, they will not overlap with each other. Does this make sense?
Yes, sir.
Okay, so the wait, whichever process grabs the wait first, will enter in the critical section. This could be any process P1 or process P2. Any value can enter in the critical section first. Now the third case, suppose A precedes D and C precedes B. So A will execute before D and C should execute before B. So the process will interleave. Process P1 completes its section A, but this should execute before section D. Process C should execute second. I mean, if the process P2 starts, then process C should execute first, then only process B should execute. This can also happen. The process may interleave in between. If this is the condition that I want to implement using semaphore, you can do that. So section A should execute first. If process P1 starting first, section A should execute first before section D. If process B2 is starting, then C should execute first before B. Before B. C should precede before B. This also you can implement using semaphore. In this case, you need two semaphores. Okay, semaphore S and semaphore T. So you will put signal S here. You will put signal T here. Okay. So after making sure that you will put weight of T here and weight of S here. So these are two semaphores, two different semaphores. This example says that A should execute before D. So section A will execute and it will put a signal till that the signal wait should happen. Okay. Yes, section D will execute only it acquires weight S. Weight S will be available only after finishing section A. When section A finished, then the signal S will be given. After signal S is given, then only the weight will be uh, released, then section D will execute. Likewise, section C will execute, but before executing section B, the T should be give the signal. The weight T is there. The T, unless T gives a signal, section B will not execute. T will be executed only after section C will give the signal T. Then only this weight will release. After section C, then section B will execute. Is this clear? So in this case, if process P2 starts, section C will start. It will give the signal T. Okay. So then section B will not work. It may interleave the process. Process P1 may start. Section A will complete its job. Then it will give the signal S. Till that point, D will not start. So A will precede D, C will precede B in this example. After giving the signal T, then the waiting period T, it will wait until C finished. And D will wait until A finished, because the signal you will get after A finished. Then only you will get enter into the section D code will start executing after getting the signal from S. That will happen only after A finished. Is this clear? Guys, you want me to repeat this? This is the last slide.
No, sir. No, sir.
Okay. So please go through the slides. The semaphore is multiple way of executing the critical section. Okay. So that's how we will implement the semaphores, which is pretty much simple. Okay. Let me upload the slide. If you have any doubts in today's class, please let me know. So it is very important the process are synchronized execution so that you will get a proper output. So that's why we are discussing the process synchronization. It will happen using mutex, semaphores. There is another concept called monitors. You can read monitors, how that will work. It is even better than the semaphore. If time permits, we'll discuss in the next class. Okay.
Yes, sir.
So other class is waiting, so I will leave now. But you can go through the PPT. If you have any doubt, you ask me on the Thursday class. So let me
Thank
upload
you,
this.
sir.
So you can check. I already uploaded the slide, lecture 20, process synchronization.